Okay, today's lecture is on kinetic energy. However, this is a term that would have been unfamiliar to Newton. Okay, it was a kind of a newer concept, right? And they didn't come up with the term kinetic energy until later. But they were interested in this quantity of motion, right, that you might think of in the following. Right here we have a speeding car headed towards a brick wall, right? It crashes into the brick wall, the bricks go flying everywhere, right? So is this just a conservation of momentum problem? Right? Because now we've got not just a ball, getting hit by another ball. This is, mortars, the mortar holding the brick together, breaking, the crushing of the hood of the car, right? And so the question is what is the oomph that this car possesses that allows it to do all of this damage, right? Now, Newton had speculated that the oomph, as we might call it, was proportional to, that's a terrible proportionality, let's try it again, was proportional to the velocity, right? Whereas others thought it might be proportional to the velocity squared. Now, Emile du Chatelet, who was basically the girlfriend of Voltaire, but an important scientist in her own right, making her own contributions, had heard of an experiment that might actually settle this issue. And this experiment involved dropping steel balls into clay. And so we can imagine that if we drop this steel ball from some height h, right, into the clay, so this is kind of the before picture, but after, what they found was that the, let's draw it like this. We don't really need this line here, do we? Find that the steel ball would embed itself, would dent the clay, right, creating a hole whose size we'll characterize by a depth delta x. Okay? And so what they found was that the delta x was proportional to the height that you drop the ball from, but that it was proportional also to the velocity squared. So if you drop the ball with twice the velocity, it would make a hole that was 4 times as deep. Okay? If you dropped it with 3 times the velocity, it would make a hole that was 9 times as deep. Okay?
Okay.
So this seems to settle the question that this oomph that causes the damage, right, this hole that it makes in the clay, is proportional to the velocity squared. Right? Let's have a look at what's going on in this situation just a little bit better here. Right? You might recall that from lecture 6, right, we had an equation that would allow us to figure out what the velocity is just before it hits the ground, right? If we drop it from a height h, right? And so this would say that the final, let's call it, we want to get a velocity here too. So I'll just call it v final squared equals v initial squared, which is 0, right? 2 times gravity times h, right? This was that equation from lecture 6, right? I'll write it up here. So v final squared equals v initial squared plus 2 times the acceleration times delta x, the displacement. Okay?
Okay.
So here our displacement is h. We drop it from a height h. We can expect that its velocity, right, is going to be proportional to the square root of 2 times g times h, right? Now, in order to get this result, right, it turns out you have to assume that the force that the clay exerts on the ball, right, so if we do a free body diagram of the ball, right, as it's impacting in the clay, there's going to be an upward directed force, we'll call it F sub c, but it's a constant, okay?
Okay.
Of course, we'll also have, mg acting in the opposite direction, right? But we can assume that mg is, actually the way we usually write this is as follows, that this constant force that the clay is exerting on the ball when it impacts, right, makes gravity negligible, okay?
Okay.
So if that's the case, then the acceleration that the steel ball will experience, right, remember that force is equal to mass times acceleration, this will be F sub c over m, where m is the mass of the steel ball, okay?
Okay.
Now, when it first enters the clay, it has this velocity here. I'm going to just call this v squared. Okay? Actually, I'm going to call it vi squared because it's the initial velocity in the second step of our problem here, right? So, and then at the end, it comes to rest, so it's got a velocity of 0, right? So we could write that 0 is equal to this initial velocity, which is in the negative direction, right? Minus vi squared, right? The force F sub c is upward directed, right? So we'll have plus 2 times this acceleration, which is Fc over m, times delta x. So this says that vi squared is equal to 2 times Fc, the constant force, over m times delta x. So you can see that delta x is proportional to the velocity squared as required, right?
Yes.
But notice that I can rearrange this a little bit, right? I'm going to move the mass over here, and I'm going to divide out the 2 so that I directly get this expression. 1/2 mass times the initial velocity squared equals the constant force times delta x. Okay? And the reason I wrote it that way is because these terms will turn out to be significant. In the next couple of lectures, we're going to develop this a little bit, and we're going to find that this term here is something we call the kinetic energy. Okay?
All right.
And this term here we call the work. Okay? And so we'll see that there's this change. Remember, the final velocity is 0, so this is also a change in the kinetic energy, right?
Yeah.
So we started out with the ball had this stuff, right? This kinetic energy, right? The oomph,
Yeah.
just before it entered the clay. And then the clay, interacting with it, brought it to rest. So it came to a complete stop. So the kinetic energy went from this full-on value here to 0, right?
All right.
And in doing so, right, work was done on the clay. The work that was done was the kind of the making of the whole. Okay?
Okay.
And so we're going to develop these concepts of kinetic energy and work in the upcoming lectures. But experimentally, right, this was, I think, the first confirmation, right, that this oomph, or kinetic energy, was proportional to the square of the velocity. Okay? So that would mean that in our car example, right, if we drive into a brick wall at, say, 20 miles per hour and we do a certain amount of damage, it's probably not a lot. It might not even knock any, it might knock our bumper off, but it wouldn't really knock any bricks loose, I don't think. But if we, doubled or tripled that speed, right, going 40 or 60 miles per hour, the damage that's done would go up, not linearly, but like the square, right? So if we went up to 40 miles per hour, we'd see 4 times the damage. If we went up to 60 miles per hour, we'd see 9 times the damage. That's almost 10 times the damage, right?
Yeah.
Order of magnitude is a big deal. So, and that kind of fits with our common sense of stuff, right? If you punch your buddy in the arm lightly, that's one thing. But if you punch him with twice the speed, right, then, he's not going to be happy. Because it doesn't just double the pain, right? It multiplies it by a factor of 4.
You want to say that again? About the arm punching?
Well, if I punch somebody in the arm lightly, right, just playfully, hey buddy, pop, right, no big deal. But if I, bah, then he's going to, if I double the speed of that punch, it magnifies the pain by a factor of 4 because the energy went up by a factor of 4.
All right, but the speed was only double.
I know, and this says that the oomph, or the kinetic energy, is proportional to the square of the speed. So if you double it, the energy goes up by 4 because the square of 2 was 4.
Okay.
If you triple the speed, it goes up to
Right.
3 squared, which is 9. So 9 times the energy. 9 times the pain. Okay?
Okay.
I think that's all I wanted to say about this particular experiment. I guess you could also show, you could substitute back in here finally, right? This initial velocity, right, you might recall, was also equal to 2gh, right? So you can also show that delta x, right, if I replace v sub I squared with this quantity here, right, 2gh is also equal to this 2fc over m times delta x. And ignoring all the other stuff, you do see that delta x is proportional to the height, right?
Okay.
So that confirms these kind of experimental findings, okay?
All right.
And that's it.